Hello friends, welcome to a new video of I Square. So far we have learned about real numbers, especially we learned about Euclid's division lemma. Also we learned about Euclid's division algorithm to find HCF of any two numbers. In this class we are going to learn about prime number factorization. Of course we know about prime numbers and composite numbers. Prime numbers are those numbers whose only divisors are that number itself and 1. Whereas composite number are those numbers who has other divisors. That is, a number which is not a prime number is of course a composite number. In this class, we are going to derive a relationship between a prime number and composite number. So, we shall begin with a composite number, say 32,760. Now we are going to factorize this number. So how we can do this? In order to factorize a number, it is enough to divide that number by its divisors. But now we are in a position to derive a relationship between a prime number and a composite number. So we are going to factorize this number in terms of its prime factors. We shall look into it. So here we have divided 32,760 by 2. First of all, we have to check that whether it is divisible by 2 or not. If it is not divisible by 2, then we should check for the next prime number 3. We know that the first prime numbers are 2, 3, 5, 7, 11, 13, etc. So we should check in this order whether this number is divisible by 2 or not. We should check that first. If it is not, then we should check for the second prime number whether this number is divisible by 3 or not. In that manner. So first of all, we have divided this number by 2 to get 16,380. Then also it is divisible by 2. So when it is divided by 2, it results in 8,190. Again it is divisible by 2. So when we divided it, it gives us 4,095. But this number is not divisible by the first prime number 2. So we should check for the next prime number. The next prime number is nothing but S, 3. So we should check whether this number is divisible by 3 or not. It is divisible by 3, and when we divide it, we get 1365. It is also not divisible by 2, and it is divisible by 3, and when we divide, it will result in 455. But this number 455 is neither divisible by 2 or 3, but it is divisible by 5. So when we divide 455 by 5, it will result in 91. But 91 is not divisible by 2 or 3 or 5, but it is divisible by the next prime number, which is 7, and it results in 13. Of course 13 itself is a prime number, so we stop our division by that. Hence when we divide this, we can pictorially represent this as like, when we divide this by 2, it will result in 16,318. Again when we divided this by 2, this resulted in 8,119. Again when we divided this by 2, it resulted in 4,095. But this is not divisible by 2 but divisible by 3, and it resulted in 1,365. Again when we divide this by 3, it will result in 455. But when we divide this by 5, it resulted in 91. And when we divided this by 7, it resulted in 13. See, each of these numbers are composite numbers and the factors are prime numbers, and such a representation of a composite number into its prime numbers, it can be named as factor tree. So if in your exams it is asked to find the or draw the factor tree of a number, you should pictorially depict the factorization process like this. So in order to pictorially represent it like this, first of all we have to divide this process, and then it is easy for us to represent it like this. Hence we can represent 32,760 like this. How many 2 erases? 3. So 2 into 2 into 2 equal 2 cube into 3 into 3 equal 3 square into 5 one time into 7 into 13. So 32,760 can be expressed as 2 cube into 3 square into 5 into 7 into 13. That is, since this expression only contains prime number, we can say that 32,760 can be expressed as a product of primes. Is it true? See, we expressed this number as a product of primes. Okay. In a similar manner, we can express any number, any composite number as a product of primes. What we should do? We should do only this kind of division process, and if necessary we can express it like a factor tree. Also we can express like in this form. Hence every composite number can be represented as a product of primes. Hence we said that every composite number can be expressed as a product of prime numbers, and this statement is named as fundamental theorem of arithmetic. That is, fundamental theorem of arithmetic states that every composite number, whatever be the number, if it is a composite number, we can represent as a product of prime numbers. Just like the previous example, we took an example 32,760 and we expressed it as 2 cube into 3 square into 5 into 13. Like that, we can always express any composite number, not that any composite number, as a product of prime numbers. This is what fundamental theorem of arithmetic says. That is, if we are given a composite number as a can be expressed as p1 raised to m1 into p2 raised to m2 into p3 raised to m3 into etc. into pn raised to mn, where m1, m2, m3 etc. mn are any integers. It can be powers, maybe 0. And p1, p2 etc. pn are prime numbers. That is every composite number. This is the algebraic form of fundamental theorem of arithmetic, where pi prime number and mi any positive integer. So the algebraic form of fundamental theorem of arithmetic can be expressed as, for any composite number a, it gets an expression of the form a is equal to p1 raised to m1 into p2 raised to m2 etc. into pn raised to mn, where pi be a prime number and mi be any positive integer. Is it clear? Now we shall check what is the use of fundamental theorem of arithmetic. The fundamental theorem of arithmetic can be used in order to find the HCF and LCM of any two numbers. We have already learned that Euclid's division algorithm can be used to find HCF and LCM of any numbers, but in most cases Euclid's division algorithm seems to be a time consuming process, because we want to express each and every number in terms of a is equal to bq plus r, and it costs us lot of time when it comes to bigger numbers. So prime number factorization method gives us a more easy method or more convenient method to find HCF and LCM of any two numbers. We shall check how we can use prime number factorization method. Suppose that we are given with two numbers, a is equal to 6 and b is equal to 20, and we are asked to find the HCF and LCM of these two numbers. In order to find the HCF and LCM of these two numbers, it is necessary to represent each number in the prime number factorization method. That is, 6 can be represented as 2 into 3, since 2 and 3 are prime numbers, and 20 can be expressed as 2 square into 5. If you find any difficulty in expressing a number like this, just go for division. 20 can be divided by 2 to give 10. Again it can be divided by 2 to give 5. Since 5 is a prime number, we stop our division by this step and we get 20 is equal to 2 square into 5. Is it clear? Now we are going to find HCF of 6, 20. It is very easy if we understand the process. To find the HCF of these two numbers, HCF means highest common factor. First of all, we should check into common prime in the expression. That is, we should check whether any prime is available as a common prime in these two expansion. See, 2 is a prime which is common to both the expression. Then we should choose the one with lowest power. Note that the one with lowest power. In this common primes, the one with lowest prime is this. Since its power is 1, its power is 2. So we choose the lowest one with 2 raised to 1 into. Then we should check, is there any other prime which is common? No, there is no other prime which is common, hence we stop our process by this. Hence HCF of 6, 20 equal to 2. So in order to find the HCF of two numbers, just locate the common primes and choose the ones with lowest powers. Then multiply them. Now we can find LCM. LCM of two numbers 6 and 20 can be evaluated as, choose the primes available in the expression. Here we have 2, 3, 2 and 5. If the primes are occurring in a common way, that is here 2 and 2 are common, then choose one with the highest power, 2 square into. If it is not common, then choose the one with highest power in any expression, that is 3 into 5, that is here 2 is common. So in order to find the LCM, here we first locate the common primes. Then here 2 is common, then we should choose one with the highest power. In this example, we chose one with lowest power. Now, then choose primes which are not common. 3 is available here, so we multiplied 3, and 5 is available here, so we multiplied 5. Then we get 4 into 3 into 5. It is equal to 12 into 5 equal to 60. So we have LCM equal to 60 and HCF is equal to 2. Also we can note that A equal to 6 and B equal to 20 implies A into B is equal to 120. Right? Also we have HCF is equal to 2, LCM equal to 60. Then HCF into LCM is equal to 60 into 2 equal to 120 also. Hence we have, whenever we are asked to find HCF and LCM of any two numbers, we can easily obtain the HCF and LCM of those two numbers by prime factorization method, as well as the product of HCF and LCM gives the product of numbers. So from this example we can have three results. 1. HCF of two numbers A and B equal to, HCF of two numbers A and B equal to product of smallest powers of common primes. Here the common primes are 2 and the smallest power is 2. So we get HCF is equal to 2 raised to 1. And in this case we don't have any other common primes, so our HCF will be 2 itself. If there is another one prime, say 5 square, then 5 and 5 are common, and one with the lowest prime is this prime. So we must choose 5 raised to 1 into our product. Is it clear? Luckily we don't have any other primes in common. So we have HCF of AB is equal to product of smallest powers of common primes. Now the second result is LCM of two numbers A and B equal to, LCM of two numbers AB is equal to product of biggest powers of each prime available in the expansion. So In finding LCM, we have to consider all the primes, not common primes, all the primes available in the expansion, and we should check whether if it is common prime, then we should choose one with the biggest power. If it is not, we should choose all other primes in the product. See, in this process we have 2 is a common prime. So in order to find the LCM, we should choose one with the highest power in the product. So 2 square has been chosen. Now 3 is not common, so we can easily choose 3 itself. 5 is also not common, so we can choose 5 itself. So in that manner we can find LCM. Clear? Now the third result is, whenever we are given with HCF and LCM, then product of HCF and LCM is equal to 120. Here 120. In the examples, the product of the two numbers is also 120. So we can generalize this result as, whenever we are given with HCF of two numbers AB into LCM of two numbers AB equal to nothing but the product of two numbers. It's an important result. Note that for exams it is a very useful result to find HCF or LCM. So we have HCF of two numbers A and B equal to product of smallest powers of common primes, whereas LCM of two numbers A and B equal to product of biggest powers of each prime. See, here we are choosing each prime available in the expansion, whereas here we are choosing common primes, smallest powers of common primes, whereas product of biggest powers of each prime available in the expansion. Is it clear? So 3 results from prime factorization is that whenever we are given with two composite numbers, we can find HCF and LCM of those two numbers just by finding the prime number factorization of those two numbers. And in order to find HCF, we should find the product of smallest powers of each common prime, not common prime. Whereas in LCM, product of biggest power of each prime, not necessarily common, each prime available in the expansion. Also note that HCF into LCM results in the product of two numbers. Is it clear? Now we shall move into the next example. So in this example, it is asked us to find HCF of 96 and 404 and hence find LCM. Not and hence, that is, we should find LCM from the HCF. Clear? So first of all, we should find the HCF of 96, 404. If it is asked in the exam, you can choose which method should be used. Whether you can choose Euclid's division algorithm or you can choose prime factorization method, unless it is not specified in the question. So we should find HCF of 96 and 404. So first of all, we should express these two numbers in the prime factorization method. So it is enough for us to divide these numbers. So we divided 96 with its prime divisors to obtain 2 5 times and 3. So we have 96 is equal to nothing but 2 raised to 5 into 3. Also 404 is divided with 2, resulted in 2 not 2, and when it is divided by 2, it resulted in 101. Note that 101 itself is a prime number, so we stops our division by that. So we have 404 is equal to 2 square into 101. Now we are asked to find the HCF of two numbers. In the previous section, we studied that in order to find the HCF of any two numbers by the prime factorization method, it is enough to find the product of smallest powers of common primes. See, here the common prime is 2. 3 is not common, 101 is not common. So HCF of 96, 404 is equal to 2 is common and the smallest power of 2 is 2 square. So we get 2 square into nothing is common, it's common, then so we stop our process of multiplication by that. So HCF of 96, 404 equal to 2 square, it is equal to 4. Now we are asked to find the LCM. Hence find the LCM. So we are intended to find the LCM using the HCF. In the previous section we learned that HCF into LCM is nothing but AB. Yes. So we have HCF into LCM is equal to AB. This is our result. Keep in mind. It is always important. Now, HCF is given by 4. So we have 4 into LCM is equal to AB. A is equal to 96, B is equal to 404. So 96 into 404. We shall rub this. So 96 into 404. Hence, LCM is equal to 96 into 404 divided by 4. Right? Okay. Now we have it is equal to 96 into 401. 4 can be represented as 101 into 4 whole divided by 4. So we can cancel 4 and 4. So we get, sorry, this is 96 equal to 96 into 101. So the answer is 9696. Hence we found the LCM and HCF very successfully. Clear? First example is express each number as the product of prime factors, and you are given with 5 numbers. We are doing only 2, but since you are able to do the rest by yourself if you understand it properly. So first example is 140. We are asked to find the prime factors of 140. So it is enough to divide this by the prime divisors. So we have 140 is equal to 2 square into 5 into 7, right? Okay. Next we have 156. Similarly, you can do prime factorization of 156 just like this. Now we have another one, 3825. We have to find the prime factorization of 3825. So how we can do this? Just like the previous examples, just do the division. Since it ends with the number 5, it is not divisible by 2, easily observable. Then it may be divisible by 3. If not, it will be divisible by 5. Since it ends with 5. So we can do this. So we get it is equal to 3 square into 5 square into 17. Okay, right. 3 square into 5 square into 17. Similarly, you can do other examples also, right? 5005. It is divisible by 5 clearly. You can repeat the process like this. Then it is given. Next example is 7429. Similarly, you can do the same process there. Clear? Then we shall move to the next question. Find the LCM and HCF of the following pairs of integers and verify that LCM into HCF equal to product of numbers. So we are in this question, we are given with 2 numbers and we are asked to find the LCM and the HCF of those 2 numbers, and we should verify our result. What is the result? HCF and into LCM of 2 numbers will always result in product of 2 numbers. Okay. Now we shall move to the next question of exercise 1.2. Second question in exercise 1.2, find the LCM and HCF of the following pairs of integers and verify that LCM into HCF is equal to product of integers. And you are given with 3 questions, sub questions. One 26 and 91, second one 510 and 92, and third one 336 and 54. We are going to do the first one, and it is simple for you to do the next 2 by the same process. So First one, find the LCM and HCF of 26 and 91. So we are asked to find the LCM as well as the HCF of 26 and 91, and also we have to verify that whether 26 into 91 is equal to HCF into LCM. Okay. So we shall represent, the first step is to represent it is in the prime factorization method. 26 is equal to 2 into 13. If you feel any difficulty in expressing any composite number into the product of primes, just do the division. Divide it by the prime factors, then you will be able to do this. So 91 is equal to, now 91 can be divided by 7 to get 13. So we have 91 is equal to 7 into 13. Now we want to find the HCF of 26 and 91. How we can find HCF of two numbers from the prime factorization method can be found out by locating the common primes and selecting the one with the least smallest power and find the product of all such primes, right? Now here 2 is not common since 2 is available here but it is not available in this expression, but 13 is common to both and the smallest power involved is 1. Since both them have the power 1, we can choose any one of them. So we have 13 into, now 7 is not common, so we have no other prime is common, so we have HCF is equal to 13. Now LCM. LCM of 26, 91 can be evaluated by, we know that LCM of any two numbers by the prime factorization method can be evaluated by finding the product of all the primes involved. If any prime is common, then choose the one with the highest power, right? Here 2 is not common, so we can directly choose 2. 13 is common and each of them have the power 1. So we can choose any one of them, 13 into. 7 is not common, so we can directly choose 7. So we have 26 into 7. So it will result in 182. So we have LCM is equal to 182 and HCF is equal to 13. Now we shall verify whether HCF into LCM is equal to 26 into 91. We have 26 into 91. So 26 into 91 is equal to 2366. Now we can evaluate HCF into LCM. HCF is equal to 13 and LCM is equal to 182. So again we obtained the product as it is equal to, so we have HCF into LCM is equal to 13 into 182, it is equal to 2366. Hence we verified that HCF into LCM will always equal to a product of those two numbers. Is it clear? Now you can it is easy for you to evaluate the next two exercises just by this process. What you have to do is first of all express those two numbers in prime factorization method. That is, you have to express each number as the product of primes. Then to find the HCF, locate the common primes and pick the one with smallest power and find the product of all such primes. Okay. To find the LCM, you have to find the product of all the primes involved. If any prime is common to both the expression, then pick one with the highest power. Now to verify HCF into LCM is equal to the product of numbers, it is enough to find the product and it is enough to find the product of HCF and LCM. If your method was correct, then the product will be the same. Okay. So now we shall move to the next question. The fifth question of example and exercise 1.2, check whether 6 raised to n can end with the digit 0 for any natural number n. So the question is, we should check whether 6 raised to n can end with the digit 0. This is the question. 6 raised to n can be end with the digit 0. What is 6 raised to n? when n is equal to 1, 6 raised to n is equal to 6. When n is equal to 2, 6 raised to n is equal to 6 square is equal to 36 and so on. You know that. So the question is whether 6 raised to n will end with the digit for some n. Clear? When n is equal to some positive integer, can it end with this digit 0? Okay. Now 6 raised to n can be expressed as 2 into 3 the whole raised to n, right? So it is equal to 2 raised to n into 3 raised to n. Since we know that a, b the whole raised to n is equal to a raised to n into b raised to n. So we have 6 raised to n is equal to 2 raised to n into 3 raised to n. Suppose that 6 raised to n can end with the digit 0. That is 6 raised to n is a number which can end with the digit 0. Since any number which ends with the digit 0 is divisible by 5. See, 10 is a number which ends with the digit 0. It is divisible by 5. Result is 2. 100 is also a number which is ending with the digit 0. It is also divisible by 5. 30 is a number which ends with the digit 0. It is also divisible by 5. 110. It is also a number which ends with the digit 0. It is also divisible by 5. So whatever be the number, if it ends with the digit 0, it is always true that it will be divisible by 5. Now, if 6 raised to n is end with the digit 0, then it must be divisible by 5. But in the prime factorization of 6 raised to n, only 2 and 3 are available. That is, 6 raised to n has only 2 and 3 as prime factors. 5 is not a prime factor of 6 raised to n. So we can conclude that 6 raised to n cannot end with the digit 0. Why? Because if 6 raised to n can end with the digit 0, 5 must be one of its prime factor. Because any number which is divisible by 5 or any number which is divisible by 5 has 5 as its prime factor, or any number which ends with the digit 0 must have 5 as its prime factor. Here 6 raised to n has 2 and 3 are the only prime factors and 5 is not a prime factor, so 6 raised to n cannot end with the digit 0. Is it clear? Okay, we shall move on to the next question. Question number 3 of exercise 1.2. Find the LCM and HCF of the following integers by applying the prime factorization method. So we have to find the HCF and LCM of the following integers. And you are given with 3 examples there. First one 12, 15 and 21. The second one 17, 23 and 29. Third one 8, 9 and 25. We are going to do the first one. The rest is very simple for you if you understand the first question properly. So we have 12, 15 and 21. We want to find the LCM as well as the HCF of 12, 15 and 21, right? Okay. Now, in order to find, this is a more special question because here we are asked to find the LCM as well as HCF of 3 numbers. So far we have done about 2 numbers. Okay. Now, the first step, the process is always the same. The first step to evaluate the HCF is equal to express each number into the product of primes. 12 is equal to 2 square into 3. As I said, if anyone feels difficulty to write number into product of primes all at once, just go for the division method. Okay. Now 15 is equal to 3 into 5. 21 is equal to 3 into 7. Now we have the prime factorization of each number. Okay. Now HCF of 12, 15, 21 is equal to, locate the common primes. Whenever we are asked to find the HCF of any 2 numbers, we want to find the common primes. Here the common prime numbers are 3, 3 and 3. So it is common. So we should choose one with the lowest power. Since all of them have the same power 1, we can choose anyone. So 3. And 5 is not common since it is not available in any other expression. 7 is not common since it is not available here and here. 2 is also not common since it is not available in here and not available here. So clearly HCF is equal to 3. Now LCM. LCM of 12, 15, 21 is equal to. It is enough for us to locate every prime number and find the product. If any prime number appears in common, choose the one with the biggest power. Okay, here 2 square is not common, so we can directly choose 2 square into 3 is common, so we should choose one with the highest power. This is so 3 into 5 is not common, so we can directly choose 5. 7 is not common, so we can directly choose 7. Hence we have 2 square into 3 into 5 into 7. So we have 4 into 3 into 5 into 7 equal to 12 into 5 into 7 equal to 60 into 7 equal to 420. Is it clear? So it is very easy to for you to do the same process like this. So it's simple. So we had completed exercise 1.2. Several questions have not been mentioned here because it is very easy for you, just like the same method we have done. Clear? So we can directly move to the next section. Now the next section is about irrational numbers. So far we have learned about prime numbers, integers, and of course real numbers. One of the most important class of numbers is irrational numbers. Of course, irrational numbers and rational numbers together constitute the real number system. So irrational number is one of the most important part of real number system. So you know what is an irrational number, right? Any number which cannot be expressed in the form of p by q can be named as an irrational number, and any number which can be expressed in the term of a in the form of p by q is a rational number. So it is a clear definition, and you have learned in your previous classes where q not equal to 0. Now we know various types of irrational numbers like pi, root 2, root 3 and root 5, etc. Now how these numbers arise, or what is the meaning of being a rational number, or how we can prove these numbers are irrational? This is the content of this class. That is, we can make or we can prove certain numbers are irrational by a sequence of logical arguments. And this is one of the most important section for your exams. Most often it seems that the questions from this section are frequently asking in your exam. So it is one of the most important section for your exam. So listen very carefully. In order to prove any number to be an irrational number, we are going to prove a theorem. That is, as a base to prove the coming problems, we need the help of a theorem, and the theorem states that. So the theorem states that if p is a prime number and a is any composite number, if p divides a square, then p will divide a. This theorem is also important for your exams. So many times it has been asked for your exams. So the theorem states that if p is a prime number and if p divides a square, if p divides a square, then p divides a. This is the most important part of the theorem. If p divides a square, then p divides a. Okay, we can prove this theorem very simply. Suppose that a is a composite number. So a is nothing but a composite number. By the fundamental theorem of arithmetic, we know that a can be represented as the product of prime numbers, right? So we have a is equal to p1 into p2 into etc. into pn by fundamental theorem of arithmetic. So by fundamental theorem of arithmetic, we can represent a is equal to p1 into p2 into etc. pn, because any prime number can be expressed as the product of prime numbers. Now any composite number can be expressed as the product of prime numbers. Hence a square is equal to P1 into P2 into etc. into Pn the whole square. It is equal to P1 square into P2 square into etc. into Pn square. Since AB the whole square equal to A square B square. Not that AB the whole square, not A plus B the whole square. Now we get like this. Now the question says that, or theorem states that, if P divides A square, that is, if P divides this, P is a prime number, and if P divides this, P1 is a prime number, P2 is a prime number, and etc. Pn is a prime number. If P divides this product, then P must divide any one of the prime factors, or if P divides the entire product, maybe P divide this, or may P divide this, or may P divide this. Suppose that P divides P1 square. If P divides the entire product, P must divide one among this product. Okay, so suppose that P divides P1 square. That is, suppose P divides P1 square. Why we are able to suppose like that? Since P divides the entire product, then P must divide one among this product, one factor among this product, and P1 square is a factor in this product, right? So P must divide anyone. We assume that P divides P1 square. Since P is a prime number and P1 is also a prime number, if P divides P1 square, then P must be equal to P1. You may feel confused. Let us sort that confusion by, or we can eliminate that confusion by looking into an example. Suppose that P1 is equal to 5, then P1 square is equal to 25. Suppose that P divides P1 square, that is, P divides 25, then P, only possibility for P is 5. Since P is a prime number and only prime factor of 25 is 5. So whenever P divides P1 square, then P must be equal to P1. So if P divides P1 square, then P must be equal to P1. Now suppose that P does not divide P1 square, then P must divide P2 square, then, or P must divide P3 square. In all the case, P will be equal to one among the primes, P1 or P2 or Pn. Since when P divides P1 square, P equal to P1. If P divides P2 square, then P equal to P2. If P divides P3 square, then P must be equal to P3. Then P is equal to P1 or P2 or etc. or Pn. P must be one among the primes. Okay. If P is equal to P1, then P divides A, since P1 is a factor of A. If P equal to P2, then P will divide A, since P2 is a factor of A. If P is equal to P3, then P will divide A, since P3 is a factor of A. In all the cases, P will divide A, since P is one among P1 or P2 or P3. Clear? So we have P will always divide A. That is, if P divides A square, then P divides A. Is it clear? If P divides A square, then P divides A. It is a very important theorem for our coming problem. So always keep in mind that for every prime number P, if P divides A square, then P will definitely divide A. Okay. Now we shall use this result to prove some numbers are irrational. How we can use that? Question: prove that root 2 is irrational. So our aim is to show that root 2 is irrational, and we have now a strong tool in our hand. Which is our tool? Whenever P is a prime and that prime divides A square, then P must divide A. That is the theorem we have proved just now. So prove that root 2 is irrational. In such questions, we are going to do a small trick. That is, we are going to assume that P is rational, root 2 is rational. Then we are going to the further set of proofs, and we found a contradiction. We find a contradiction. Then we can clearly state that our assumption was wrong. What was our assumption? Root 2 is rational. If our assumption root 2 is rational is wrong, then root 2 must be irrational. So our logical sequencing or sequence forms like this. Steps goes on like this. We will assume that root 2 is rational. So assume root 2 is rational. So we assumed that root 2 is rational, and after to the end of the problem we see a big contradiction. Okay, then we can say that our assumption is wrong. If root 2 is rational is wrong, then root 2 must be irrational. Okay, assume that root 2 is rational. Then any rational number can be expressed of the form a by a by b. So root 2 is a rational number and root 2 can be expressed of the form a by b. And suppose that we cancelled all the common terms and we get p by q. See, if 4 by 12 is a number, after cancelling we get 4 and 12, we get 1 by 3. Similarly, we cancelled all the common factors from a by b to get p by q. Now p and q doesn't have any common factor. So we have root 2 is equal to p by q now. Okay, root 2 equal to p by q, which implies q root 2 is equal to p. We cross multiplied q to root 2. So we get q root 2 is equal to p. Now we are going to do is, now we are going to square both sides, which will result in q square 2 equal to p square. We squared to get q square and root 2 square will be 2 equal to p square. See, from this we can see that 2 is a factor of p square. Clear? Since q square into 2 equal to p square means that 2 is a factor of p square, or which implies that 2 divides p square. Since 2 is a factor of p square, 2 divides p square. Now, if 2 divides p square, then 2 divides what? P by our previous theorem, since p is a prime number. If 2 divides p square, sorry, p is not a prime number, p is any number. If 2 divides a square, then 2 divides a. That was our theorem. Then 2 divides p square, then 2 will divide p. Okay, then 2 divides p. Then we have p is equal to some 2c. Clear? Then we can write p equal to some 2c. Since 2 divides p, 2 will be a factor of p. Hence we can write p is equal to 2c. For example, 5 divides 10. So we can write 10 is equal to 5 into 2. Similarly, 2 divides p. So we can write p is equal to 2 into c, some c, whatever be any number. So p is equal to 2c. Now we are going to substitute p equal to 2c here. So we will get, when substituting, q square into 2 is equal to 2c the whole square. Since p is equal to 2c, here we have p square on substituting, which implies q square into 2 equal to 4c square. So we can cancel out 2. So we have q square equal to 2c square, which implies 2 divides q square, since q square equal to 2c square, by the similar argument as here. 2 divides q square, which implies 2 divides q by our, 2 divides q by our theorem. What is our theorem? Whenever any prime number divides a square, then that prime number will divide a. Here 2 divides q square, so 2 divides q. Note that here p and q are not prime numbers, any integers which can be written in the form p by q. So 2 divides q. Clear? Then we get a contradiction. Since When we return root 2 equal to a by b, we cancelled all the common terms to get p by q. Now p and q do not have any common term, right? Here we get 2 divides q as well as 2 divides p. See, 2 divides q as well as 2 divides p, which means 2 is a common term to p and q, which is a contradiction because here we have assumed that p and q do not have any common term. So, and we now got 2 divides q as well as 2 divides p, hence we will reach it 2 is a common term to both p and q, which is a contradiction. Hence we can conclude that root 2 is nothing but irrational. We assumed that root 2 is rational and we reached at a contradiction, hence we can conclude that root 2 is nothing but irrational. So in this problem, first of all we assumed that root 2 is rational, then we moved into these steps and we reached at a contradiction, hence we can assume that our assumption is wrong. What was our assumption? Root 2 is rational, hence our assumption is wrong, hence root 2 is irrational. Clear? So shall we move to the problem section? The first question of exercise 1.3, prove that root 5 is irrational. Question, prove that root 5 is irrational. Now you are able to prove this by the proof just like the previous proof. First of all we have to assume root 5 is rational. Then root 5 is equal to sum a by b. Cancelling all the common terms we have, root 5 is equal to r by s. Now r and s have no common terms. Okay. Now cross multiplying we get, just like the previous problem, we get s root 5 equal to r, which implies on squaring we get s square, this is s square into 5 equal to r square on squaring. Okay, which implies s square into 5 equal to r square, which means 5 is a factor of, or 5 divides as r square, 5 divides r square, which implies if 5 divides r square, then 5 must divide, yes, r, then 5 divide r by our theorem, okay. Now 5 divides r, which implies r can be written in the form of some 5c. Okay, now we are going to substitute this value of r here. So we have s square into 5 equal to 5c the whole square by substituting. Okay, which implies s square into 5 equal to 25c, which implies s square equal to 5c square. We cancelled 5 from both the sides. Okay, s square equal to 5c square, which means 5 divides s square, since s square equal to 5 into c square and 5 is a factor of s square. So we have 5 divides s square, which implies by our theorem 5 divides s by theorem. Okay, see, we assumed that r and s do not have any common factor, but on moving to the proof we get 5 divides r as well as 5 divides s, which means that 5 is a factor of both r as well as s, which is a contradiction. Okay, so we have our assumption is wrong. What was our assumption? Root 5 is rational. So what is true? Root 5 will be irrational. Is it clear? Just go through the steps of this problem. The next question, example 2 of exercise 1.3. Prove that 3 plus 2 root 5 is irrational. 3 plus 2 root 5 is irrational. This is what we want to prove. Suppose that 3 plus 2 root 5 is rational. So we have 3 plus 2 root 5 can be expressed of the form a by b. Okay. Now we have 2 root 5 is equal to, this is a little bit different procedure from the previous problems. So look it carefully. 2 root 5 is equal to a by b minus 3. It is equal to a minus 3b divided by b, which implies root 5 is equal to a minus 3b divided by 2b. Okay. We can write it as a by 2b minus 3 by 2 since b cancels. Okay. Now, since a and b are integers, a by b will be a rational number. Okay. Now, since 3 and 2 are integers, 3 by 2 will be a rational number. The difference of two rational numbers will be a rational number. So, the right hand side of the equation will be a rational number. Hence, the left hand side also must be a rational number. But root 5 is irrational. We proved it earlier. So, this is a contradiction. Since our LHS is irrational and RHS is rational, hence the equation is not valid and our assumption was wrong. What was our assumption? 3 plus 2 root 5 will be a rational number is wrong. So, what we have 3 plus 2 root 5 will be irrational. Is it clear? We shall move to the next question. Example 3 of exercise 1.3. Prove that the following are irrationals. First one, 1 by root 2. 1 by root 2. Suppose that 1 by root 2 is irrational. Suppose that 1 by root 2 is rational. Okay. Which implies 1 by root 2 is equal to what? A by b. Which implies root 2 is equal to b by a. Now b and a are integers. B by a will be a rational number, but root 2 is irrational by our previous proof. So we have root 2 equal to b by a is not valid relation since LHS is not a rational number whereas RHS is a rational number, hence it is a contradiction. Which implies 1 by root 2 is rational. Sorry, irrational. Hence, we can conclude that 1 by root 2 is an irrational number. Similarly, you can prove that 7 root 5 is an irrational number. 6 plus root 2 is an irrational number. So, that's the end of this section. Thank you for watching. If you have any doubts regarding these problems or this topic, you can comment it on the comment section. We will rectify it with our new video. You can also contact us on Instagram. We will clear your doubts directly. Thank you.